Hi, and welcome to Allen High School's discussion of bonding at the pre-AP or 10th grade chemistry level. We're just beginning our introduction into bonding, and we're going to be discussing three types of bonding. These aren't the only types of bonding. Actually, others are kind of a nuance or a variation on a theme, and we will talk about those when we get to AP chemistry. Now, before we do that, I want to draw what is called a potential energy curve. So if I have two atoms that are very, very far apart, so this is their distance apart. As these two atoms get closer and closer together, their attraction becomes realized. So there's less potential for attraction because that attraction has been realized. So they get closer together, and what happens is the electrons on one atom begin to be attracted to the electrons on the other atom. So the electrons from this guy begin to like that nucleus, the electrons on this guy begin to like that nucleus. And they reach a point at which there is a very low potential energy. So when you're at a minimum of potential energy, that's stable. And they reach a stable bonding situation. If you try to push them together too close, it's almost like an unhealthy relationship. They begin to repel one another. So this up here is zero potential energy, and it becomes more and more negative as they become more and more attracted to one another, and the attraction becomes realized. So then the question becomes, how do those electrons behave as they get closer and closer together? Well, in ionic bonding, the electrons are actually exchanged. The metal ions actually give electrons to the nonmetal. So then we have a positive cation, Ca positive ion, and a negative anion, a negative ion. Do you see how the words give you a glimpse of what we're talking about? Now, when you have positives and negatives near one another, you have an electrostatic attraction. So a positive-negative attraction is called an electrostatic attraction. So I'm going to be looking for some of these words to make sure you watch these videos. Okay? Now, in a covalent bond, rather than a complete exchange of electrons, what we have here is a sharing of electrons. You can see it in your picture right here. I'll draw it bigger. What we'll show it as is this. You have your hydrogen and your oxygen there, and they're going to share their electrons. Now, honestly, oxygen's a little piggy. It likes electrons a little bit more. It's a little more electronegative. So they're going to be closer than to the oxygen, but they're not given away. They're still shared. So sometimes they're shared evenly, and sometimes, as in this case, they're shared unevenly. And we'll talk about that in more depth when we get into covalent bonding in more detail. This is just a quick overview. Now, with metals, what you have is the valence electrons are freed up to move. It's kind of like a commune where they can, play it any house they want. So you end up with positive ions in a lattice. So if you kind of drew lines through those positive ions, it would look a little bit like a lattice fence. All right, so you have positive ions in a lattice, and those valence electrons are free to move. That's why it's called a C, because there's movements. That freedom of motion is called delocalized. So we have delocalized, whoops, my Mimio's jumping again, sorry. Delocalized electrons. They're not stuck in one location. They're free to move throughout. All right? So delocalized. I hope you can read that. Every once in a while, my Mimio goes a little crazy. All right. Now, let's zero in on the top two. That's about all we're going to say right now about metallic, is that you have positive ions that are attracted to a sea of delocalized electrons. Let's look in more detail at our ionic structure. Again, remember we have positive cations and negative anions, and again, it's in a rigid lattice. Electrons are actually transferred, not shared, not just freed up, but permanently, not delocalized, but permanently transferred from one species to another. Okay? Now, how big this crystal will be, these make crystals, like a salt crystal, this is table salt. How big these will be depend upon where you crack the crystal. So when we represent these, we look at the lowest whole number ratio where we have a neutral. So a plus and a minus equals a 0. So we're going to call that a formula unit. So we're going to represent these as a formula unit, the lowest whole number ratio that makes it neutral. Because we can't represent exactly how many there are. It depends on where we crack the crystal. Now, there's two ways we're going to be looking at it. Most of the time, we're going to be looking at the predictions of these. And for the predictions, you want to be able to classify from the periodic table. And you need to know that your metals are on the left-hand side. So if you have a metal cation present, it's ionic. The anion can either be a single element, non-metal, like that, or you're now learning your polyatomic ions, which is NO3. Wow, this is jumping. Sorry, NO3 negative. Okay? All right. Wonder if I forked out the bucks to spend some money on my little writing utensil if I would have less problems. Okay, now the other thing it can be in addition to sodium is one of your polyatomics is positive. And even though these are both nonmetals, when you put them together, they make a polyatomic cation, and any cation can be attracted to an anion in an ionic bond. Okay, so that's how we predict. And that's what you'll do most of the time. And that's also you're going to find in a later unit how we name them is by the predicting method. There are times, though, when we want a little bit more of a nuance. Here's the deal. When you do these bonding type structures, whoops, my pen's stuck. All right, when you do these bonding type structures, we really have a continuum. It's much like the continuum of behaviors that we call like OCD and ADD, right? We have what somebody has defined as normal, and you know, who gets to make these definitions anyway? So this is normal. And then there's somebody draws a line and they say, hey, you're on this end of normal, you're too ADD. It's interfering with your life. And maybe you're on this end of the continuum and it's OCD. And again, who defines those boundaries? But somebody does. Somebody sets a boundary and says, okay, this is it. At that point, it's interfering with your ability to function in school, work, home life, social life. And we do that with ADD. I'm not saying whether it's right or wrong. That is the reality. Okay, that's what we do here, is we look at this continuum, and we're going to take the difference in electronegativity values. You'll be given those, and that difference in electronegativity goes from 4.0, and then we're going to draw a line in the sand at 1.7, and then we're going to draw another line in the sand at 0.3, and then at 0. All right? And then what we do is we say, okay, if we take the difference in electronegativity, we're just going to take the big number and take away the small number. If it's 1.7 and greater, we're going to calculate it that it's ionic. And the reason we do that is because scientists have found that above 1.7, it behaves as if it's ionic. And we're going to look at those properties. It has the properties of ionic. Now, between those, it's more shared, but it's unequally shared. So we're going to call this polar covalent. Wow, you're really having to put up with some crummy handwriting with this Mimeo today. I don't know what's up with it. Polar covalent. Oh my goodness. Look at that. That's craziness. All right, let me just see if I can erase that. So let's try this again. So we've got our line. And 1.7 to 0.3, we call that polar covalent. And below that, we call that non-polar covalent. Okay? And only calculate this when you are asked to calculate this. And I don't happen to have those numbers handy, so I'm going to ask you guys right at the beginning of class to remind me, let's calculate that. Let me show you that in class. But all we do is look up these electronegativity values and we subtract them. It's that simple. And when we do beryllium iodide, we're only going to look at one of the bonds. There's bonds on either side. And we're going to look at one bond when we calculate this. So we'll do that in class. Until then, this is, if I can even write it, your best chem teacher signing off.